In this video, we'll talk about some ideas for how we could find the derivative of inverse function, given we know the derivative of the function itself. So inverse functions are defined that way. They are the inverse or the undoing of a function itself. So f inverse is defined that if I compose f with f inverse, I just get x back, or I can just go the other way around too. F inverse of f of x also gives me x. It's a function that sort of undoes what f did in the first place. Another way you can think about this is that the graph of f inverse is the graph of f reflected over the line y equals x. Picture something like this. I take the line y equals x here in the middle. If my function graph lives down here, the inverse graph is just reflected over this line, lives up here up top. What could this mean for derivatives? Well, if I take a point here, and look at this tangent line, if I reflect that, I get up here and I get this tangent line. It looks like if one of those lines is really steep, the other would be really shallow, and vice versa. That's actually what ends up happening here because of how the functions work. A way we can figure this out using calculus is by setting up how I want to differentiate this function. So I want to differentiate y equals f inverse of x. How can I do this? Well, I know how to differentiate f, so if I had f and not f inverse, I'd be okay. So what I can do is I can apply the function f to both sides, and that will give me that f of y equals x. But this I can differentiate using implicit differentiation. This is some equation involving x and y where you don't have y equals stuff, you have something else. So I can differentiate this, and if I do that, I would get f prime of y times dy dx equals 1, or dy dx equals 1 over f prime at y, which illustrates the picture we had above in the fact that if one line was really shallow, i.e. f prime had a low slope that was close to 0, then the slope of y, which was my function up top here, f inverse, would be really steep because it's 1 over a small number. So what do we get from this? Well, we get then that for y equals f inverse of x, dy dx equals 1 over f prime at y. And that's our general formula. To be more particular about how we apply this, we're going to say the following. So we assume we're looking at a point x equals b, and let a equal f inverse of b, which is the same thing as saying that f of a equals b, meaning that b is actually in the domain of f inverse. Then the derivative of f inverse at the point b equals 1 over f prime at a, which might not be entirely helpful, but because a is f inverse of b, this is 1 over f prime of f inverse of b. So if I want to find the derivative of an inverse function at a point, I find the derivative of the actual function, I take 1 over that, and what I plug in to that derivative is f inverse of the point that I'm looking at. This is the generic idea and a generic formula for finding derivatives of inverse functions. There'll be many examples that we'll see of exactly how this works, and we'll see why this comes into play as we solve out for these functions.